All right, this lecture today, we are going to be talking about systems of equations in two variables. And this is a nice lecture to follow. We just talked about how to graph lines. And so we're kind of jumping out of order a little bit from the book, but this is a good section right now because when we look at systems of equations of two variables, we can think of the solutions graphically or we can find them algebraically. Now, pretty much we'll do it algebraically, but it's important to look at it graphically also. So, just a quick definition. A system of equations, so it doesn't have to be just two, but we're just going to look at two for right now. So a system of equations, okay, it's composed of two or more equations. Gotta have more than one, right, if we're going to have a system. So it's composed of two or more equations considered simultaneously. So what that means is I am going to, well, hold on. Let me try and spell. And then let me give you an example of one. So, for example, if I had like x minus y equals -5 and x plus 4y equals 0, let's say. So this is my system, and what I'm looking for is we're going to assume whatever my solution is, or is there one, is there none, are there an infinite number? Assume that x and y satisfy, or are solutions to satisfy both equations at the same time. So that's what they mean by simultaneously. We want my x and y to satisfy both of them. If I find an x and y that is a solution to the first equation, but it's not a solution to the second, then I can't say it's a solution to this system, okay? So for something like this, let's talk about what could possibly happen. So this is a line, right? I could get this into the form y equals mx plus b, and this is also a line. So if I were to graph, or if I were to get this into the form y equals mx plus b, I'm going to add y to the right side and add 5 to the left. So I get y equals x plus 5. And then if I solve here, I get y equals a -1/4 x, right? If I move that x over and then divide by 4. So I have, sorry, my throat is a little scratchy today. It's because I have children and they're little germ factories. So it's spreading around our house. So it's good that this is all online and not face-to-face. So what would happen? What would happen? This is going to be exciting. Aren't you excited? I'm excited as well. We're going to see what happens when I graph these two lines. Because, you know, if we can graph it, why wouldn't we? We might as well. What else are we going to do? Huh? I'm sure there's nothing else on YouTube you would like to watch besides me graphing a couple of lines and see what happens. And remember, I can't draw lines, so whatever this is, pretend it's a line. All right, let's look at this equation right here. X plus 5. So I'm going to go up 5, 1, 2, 3, 4, 5, right? There's my y-intercept. What is my slope? My slope is 1. So I can go up 1 over 1, or I could go down 1 into the left 1. I think I'm going to do that just because of how I drew my axes here. We're 1, 2, 3, 4. I should be at 0 at like -5. Close enough. Man, my lines are just absolutely horrible. I'm doing all this on a surface and my lines are horrible. So let's look at this guy. What's my y-intercept? It's 0. Okay, and then what is my, what do I have here for my slope? It's a -1/4. So I could go, you know, up 1 and to the left 4. And I'm probably going to be right about there. Or I could go down 1 and to the right 4 and I'm going to be there. So if I draw this, let's see if I can. Oh, that was a little better. I turned my computer. Oh, maybe not. Maybe that's not better. Anyway, you get the idea. What do you notice here? This is supposed to intersect at this point right here. And what do I know? So what is this point? This point is a -4, 1. So what that tells me, this point, remember, lies on the purple line and it lies on the yellow line. So that means that that point, negative 4, 1, is a solution to the purple line equation and to the yellow line equation. So that means that it's going to be a solution to my system. And I sure can look at that and see, you know, if I plug in for the purple, if I plug in 1 for y, does that equal, right, negative 4 plus 5? Oh, look at it, sure does. Isn't that amazing? And then if I plug in 1 for y on the bottom, and I take a negative 1/4 times negative 4, does that equal 1? It sure does. So this is exciting. I'm excited. You're excited, I can tell. So we have solved the system. We have solved the system. And if we look at this system, we've solved the system, and what we say is that the system is consistent. So we'll write down those definitions here in a moment. Let's look at what else could happen. Because remember, if we're dealing with this graphically, you know, other stuff could happen. So if I think about lines, I mean, we could have lines that, so let's just say solve graphically. What could lines do? So they could intersect in one point. They could be parallel, which means we have no solution, or they could be the same line, which means we have an infinite number of solutions. So I just want to show you some examples of where they might be like parallel or something, or maybe they're exactly the same line. So let's solve graphically. I want to do x minus 3y equals 1 and negative 2x plus 6y equals 5. So if I were to graph this might be a little bit tricky because I'm not going to get the best y-intercept here, but let's have this one be my purple one. So I would get y equals, I think, a negative 1. No, it's not going to be negative. The problem is doing this in my head, which isn't always good. I'm going to make that purple a little lighter so maybe you can see it a little bit better. Maybe not. Yeah, that's a little bit better, huh? So, all right, so y equals what? 1/3 x minus 1/3. So that's going to be a little tricky to graph, but I'm not worried about it. I might just take its intercepts or something. And then here I'm going to get y. So if you notice, putting it into slope-intercept form is not necessarily always the best way to do it. But I've already committed, so let's do it. All right. So I'm going to graph these guys. Let's look at, whoops. Well, you can see, I mean, if you're looking at this and if you're thinking about it, I know that I'm asking a lot, having you think, I get that. But, you know, in college, that's kind of what you're supposed to do. If I look at this purple line right here, I should have done that one in yellow. What do you notice? What's the slope of this line? It's 1/3. And look at this line right here. The slope of this line is also 1/3. So if I graph these, my x-intercept, let's see, for this first one, if y is 0, x is going to be 1. So if I know I go through 0, 1, so I just basically set y equal to 0 to kind of see where I'm at. And then I know that my slope is 1/3. So I'm going to come up 1/3. Right? Or I could go down 1 and to the left 3. And I get this line right here. So now, sorry, I should have written this one in yellow. Let's do this one in yellow here. If I look at this, my intercepts aren't going to be super easy to figure out. So I'm just going to kind of try and graph this. My intercept is 5, 6. So that means I'm almost at 1. Right? And then I'm going to go up 1 and to the right 3. And then I'm going to come down 1, right, and to the left 3. So what do you notice if you look at something like this? We pretend these two are parallel. They're parallel lines. They have the same slope. So remember what I want with this system of equations. I want a point that satisfies both equations, which means I need a point that lies on the yellow line and I need a point that lies on the purple line. Obviously, that's not going to happen. So what do we know about this system? There is no solution. Oh, wah, wah, wah. No solution, okay? So that's what we mean by something that has no solution. If it has no solutions, we say it's an inconsistent system. We'll write these down So no solution means it's inconsistent. We can't consider these simultaneously. It doesn't work. There's no solution to it, which is all right. Guys, that happens, you know? Sometimes that happens. The last example I want to show you is kind of interesting. So let's look at one more example. Let's solve graphically. Whoops, thought I grabbed the eraser there. Okay, so one more with graphically and then we'll call it good. 2x plus 3y equals 6. 4x plus 6y equals 12. And I'm going to graph these just using intercepts. So let's look at these two. So if I graph these using intercepts, I think that'll be the easiest instead of trying to solve for y. Okay, make my little Cartesian coordinate system. Thank you, Descartes. If x is 0, y is 2, so I am up at 2. If y is 0, x is 3, so I have 2 and 3 as my intercepts. So I have this line. Look at you guys, my lines are getting better. Okay, maybe not, but I like to think so. And then let's look at the yellow one. So if I let y be 0, then x is 3. Oh, look at this, interesting. And if I let y be 0, x is 3. If I let x be 0, y is 2. You guys, look at this. So I get basically the same line. And if you divide this second guy, this whole equation right here, divide it by 2, what you'll see is you're just going to get that equation right there. So my system here is really just asking, what solutions satisfy both these equations? Well, they're the same equation. So how many solutions am I going to have? I'm going to have an infinite number of solutions, right? Because I can take any point on this line, they're the same line, and I have an infinite number of solutions. So that's one time that we can get an infinite number of solutions, and that's okay too. That's all right if we have an infinite number of solutions. Now, so my solutions aren't just anything, okay? My solution is going to has to actually be on this line. So it's not that I get like all of the plane. I get all the points that lie on this line. So we have an infinite number. And how do we say we have infinite solutions? Well, there has to be some way that we can relate these. So what I'm going to do is I got to talk about, though, I have an infinite number of solutions, but I need to be specific about how x and y are related. So I'm going to solve for y really quick. And I'm going to say that my solutions are all of the form x, comma, so I can pick any x I want, but remember my y value has to be forced, right, to have this relationship. So here are my solutions. This is one way to describe the solution set of something like this, where I have two lines basically on top of each other, so it's the same thing, okay? This is also a consistent system, but what we say is that it has a dependent. That it's dependent because we're depending on, I don't have an infinite number of solutions unless I grab whatever I want for x, and then my y is dependent on x. The other one that we had where we only had one solution is called a consistent independent system. So let's write that down a little bit more precisely with the consistent and inconsistent. You know, I mean, I'm going to write it down for you. You'll have some of it on your homework. I'm not super worried that you know these completely, but if a system is, whoa, that was crazy. If a system is consistent, then it has at least one solution. I'm going to be lazy here. If a system, so that is going to include, so remember the things that we can have, right? What can happen with lines? They either intersect, they are either can be parallel, or they can be the same line, right? That's what we've seen can happen. Oh, there's an I in there. Pretend there's an I in there. So if they intersect, they're going to be consistent. If they're parallel, we say they're inconsistent, which means no solution. Now, if it's independent, That means I'm just going to say there's one solution here. I'm being a little bit lazy. Like maybe this isn't technically the right definition, but if we say it's dependent, that means that, well, what that really means is that I can get one equation from the other by just multiplying by a factor or dividing by a factor. So dependent means I have an infinite number of solutions because we end up having the same line. So when you're looking at your solutions, you're going to either say they're consistent or inconsistent. If it's consistent, then you say it's either independent or dependent. So I hope that makes sense. All right. Do we want to graph these every single time I want to solve a system like this? No, I don't want to. I don't know about you, although I like graphing, so I probably wouldn't mind it. But it's not always the easiest way to do this. So let's talk about solving systems algebraically. Now, I am going to show you two different ways to do this. I don't care which way you use. Honestly, if you want to use substitution every time, if you want to use elimination every time, that is fine. So even if your homework tells you to use one, I don't care which one you use. I just want you to choose one that you like. Sometimes it's going to be easier to do one rather than the other, but you can choose. I think I spelled algebraically wrong. I think I had this issue in the last one. So let's first talk about substitution. And basically, I'm just going to do a bunch of examples for you. Okay, so substitution. My first example here for you, let's go back to that one we had before. Ooh, we can see that we really did it right. X equals negative 4y. So substitution, what substitution does, again, this is what I love about mathematicians. If they say it's substitution, guess what you're going to do? You're going to substitute. Because if anything, we are blunt and we just say what we mean, okay? So if I know that x is equal to negative 4y. So I'm going to take this negative 4y and I am going to substitute it in for x here. People, look. This is x and this is x. So we're going to substitute that in. So instead of having x, I'm going to have negative 4y minus y equals negative 5. Now I have a system with just one variable, which is what I want. So I have a negative 5y equals negative 5. Sure enough, y equals 1. Now how do I get x? Remember, my solution should be an ordered pair. So how do I get x here? Well, I know x is equal to a negative 4 times y. So I know y is 1, so x is negative 4. So what is my solution? My solution is negative 4, 1, which we saw before graphically. This tells me it's a consistent system because it has a solution, and it's independent because it has only just one. Independent because the solution does not depend on, it's just one solution. That's it. I don't have a bunch of x's and then the y's depend on what x is. This is just it. Consistent and independent. So that is what substitution does. Let's look at another one. It doesn't. Okay. Oh my goodness. Calm down. All right. So let's look at another example of substitution. Sorry. There we go. What if we had the system y equals, and I should be saying in here like solve, but I think you know that, hopefully. Substitution is really a good method to use if you have one of your variables already isolated. So by that, notice I have that y is equal to this 2x minus 6. So I'm going to substitute that in for my y here. So I'm just going to rewrite the bottom equation as 5x minus 3 times 2x minus 6 equals 16. And now again, I have an equation with only one variable, which makes it much easier to solve. I get 5x minus 6x, what would that be? Plus 18, don't forget to carry the negative, equals 16. So I have a negative x, subtract the 18 equals negative 2. So I get x equals 2. Now, how do I find y? Well, the great thing is when you do substitution, you already have y by itself. So we know that y is equal to 2 times x. Well, I know x now is 2 minus 6. So I have 4 minus 6, which is a negative 2. So what is my solution? 2, negative 2. I need to write it as an ordered pair. And what type of system is this? It's consistent because it has a solution, and because it only has one solution, it's independent. Okay, let's do another one. One more of the substitution, and then we'll try something else. I want to try one maybe that's a little bit more interesting than that. So sorry for the pause. Let me see. How about this one? So x minus 2y equals 3. 2x equals 4y plus 6. Okay, so I want to do substitution again. What am I going to substitute in? I'm probably just going to really quick divide this guy by 2. And what does that tell me? That x equals 2y plus 3. And you might see what's going on already, but pretend you don't. And I'm going to take this x and I'm going to use the other equation. Listen, don't substitute this guy back into here. It's just, you haven't done anything. So I'm going to substitute it back into this equation. Now this one's going to be interesting because we're going to get some stuff going on here. But I would have 2y plus 3. That's going to be my x. Then I have the minus 2y again. That's my x, right? Minus 2y, and then this whole thing is going to equal 3. So I wanted to do one like this because you kind of see what happens. This is really cool. Look at my 2y's cancel and I get 3 equals 3. So look at what we're asking. We're saying for what y values does 3 equal 3? Well, 3 always equals 3 as far as I know, unless something changed over the weekend. I don't think it did. 3 always equals 3. So what this tells me is I have the same line for this. So I am going to kind of write down what I already have my x solved for here. So I have an infinite number of solutions. Infinite solutions. I know there's an E there. So this is a consistent dependent system. And then how do I describe my solutions? Well, look, I already have x solved for you guys. So why do more work? So I'm going to say that my x is going to be 2y plus 3 for any y you give me. So look at, again, that just forces that relationship between x and y. So now I'm saying for any y you give me, my x will be 2y plus 3. Could you come back up here if that is uncomfortable for you to leave it in terms of y being the independent, kind of the independent variable here? You are welcome to solve for y and then put x and then whatever x or y is equal to. But that's an example. If I graph this, these guys would be the same line. Okay, guys. So let's talk about the other algebraic way. This is probably my favorite way. I know you shouldn't have a favorite, right? Kind of like your kids, you shouldn't have a favorite way, but I kind of like to do elimination, although sometimes substitution just makes more sense. So again, if mathematicians are calling this elimination, what are we probably going to do? We are probably going to be eliminating a variable. And that's kind of what I love about this. I don't know, maybe that's, what does that say about me? Maybe nothing good, but I really like solving ones using elimination just because I think it's kind of fun to get rid of one of the variables right away. So when you look at elimination, what we want to do is we're going to basically add or subtract the equations together. So I'm literally just going to add these equations together. And when you do this, your goal is to eliminate one of the variables. So in this case, you can see if I add this, I'm just going to add straight down, basically combining like terms. Look at, if I add 3x and a negative 3x, it goes away. So with elimination, if you see that like one of your variables is just the opposite of the other variable, that's a really good indication that elimination will work well. Because these guys now cancel. What am I going to be left with? 4y minus 5y is a negative y. Negative 2 plus 1 is a negative 1. So look at what we get. Right away we get y equals 1. That's it's an easy way to do this. Sometimes when we use elimination, and I'll show you one, we might have to like multiply maybe by another number so that I get some cancellation happening. But especially if you have like one, either your coefficients are the same and you can just multiply by a negative, or let's say that your coefficients, one is positive and one is negative, and it's easy to get that other coefficient in there. That's when elimination is super useful. Now that I know that y is 1, though, I have to figure out what x is. So what I want to do is remember that y has to satisfy both of these equations. So I'm going to just pick one of them. I'm going to pick the top one. So I know that 3x, sorry, I keep meaning to do a lighter color. 3x plus 4, what is y now? I know y is 1, equals negative 2. So that tells me 3x equals, subtract the 4 and negative 6. So x equals negative 2. So for elimination on the back side of the process, it's a little bit longer because you don't have a variable solved for explicitly, but I still kind of like it, you know? So consistent independent system. Let's do another one. So another example might be something like this. X plus 3y equals 0, and 20x minus 15y equals 75, okay? So why would we want to do, now I think you could argue that substitution would be quite easy with this one. You could just subtract the 3y, right, and plug it in for x there. But I want, because it's new, I'm going to multiply this guy by, look at the y's, I want to get rid of the y's because this is negative and this is positive. I'm going to multiply the entire equation by 5. The entire equation, now it's not going to look like it because the right hand side is going to be 0, but I'm going to multiply everything by 5 and then I'm going to rewrite that equation. Whoops, that's not what I wanted. I'm going to rewrite that equation on the bottom here. So I would get 5x. Now look at why I wanted to do that, because I get a positive 15y and now those y's are going to cancel. 0 times 5 is 0 last time I checked. So I'm going to add these two equations. I get 25x, right? These guys cancel, equals 75. And so I get x equals 3. Then I'm going to come back. I can grab either equation and I'm going to grab this equation because it seems like the easiest to work with. So I would have 3 plus 3y equals 0. So I get 3y equals a negative 3. So look at that. Y equals negative 1. Now we're cooking with gas. Now we got this going. So we got 3 comma negative 1 is my solution. This is a consistent, independent solution. Okay, so that's what's kind of nice about elimination is it kind of works out well. So let's try one more. I want to do one more. Excuse me, my throat. I want to do one more that might be kind of fun. Well, let's just try this one. 2x plus 6y equals 7. 3x plus 9y equals 10. Now this one is actually a pretty good candidate for elimination. Even though I don't have the opposite signs or anything, if you notice if I tried to solve this to do substitution, like if I tried to solve for y or x, I'm going to get some fractions. Not that I'm scared of fractions. I'm not. However, it's just maybe going to get a little bit messy. So I'm going to go ahead and work with my x's because they're just the smaller number. And what I want is I want my x's to have the same coefficient just off by a sign. So I'm going to multiply this guy by 3. And then I'm going to multiply the bottom one by negative 2. So do you see how if I multiply this guy by 3, that gives me 6 right here. If I multiply this one by negative 2, I get a negative 6, and then they will cancel. So if I do that, on the top, I'm going to get 6x plus 18y, right, equals 21. Oh, good. This is going to do what I wanted it to do. On the bottom, I get negative 6x minus 18y equals negative 20. So this is pretty cool, huh? You're like, but Sarah, look at what's going to happen. I know it's exciting, isn't it? If I look at this, again, I was focusing on getting rid of my x's, but look at what ends up happening. My x's cancel and my y's cancel. So what do I have on the left-hand side? I have nothing, which is also known as 0. What do I have on the right-hand side? I have 1. So you guys, look at what this is asking you to do. It's asking you to find an x and a y value that will make 0 equal to 1. Well, I hate to tell you, but that's not possible. So we have no solution. So this is an inconsistent system. So what do you know about these lines? They are parallel lines. They have the same slope, but they have different y-intercepts. Pretty cool, huh? I like doing those. So again, I don't care if you use substitution or elimination. I actually will say, you know, use either one. Your homework might specifically tell you to use one of them, and it's probably good to try both of them, but I'm good with whatever one you really want to do. All right, let's talk about applications. Applications is a fancy way of saying word problems. These are really fun. I love doing applications. That probably doesn't surprise you. So let's see. I want to do let's start off with something that's a little easier. Actually, might steal one from your book. All right. I don't know. We'll just start off with example tickets to a concert sell, let's say, for $12 for an adult. Oops. And let's say $10 for a child. Okay. If 25 people from a school attend the concert and pay a total of $260 for the tickets, how many were adults and how many were children? Sorry, a lot of writing. Were children. Okay, so we have some people from a school, so I didn't write this out perfectly, but they're going to a concert. They're going to take some adult teachers. They're going to take some kids. And we know that the tickets are $12 for an adult, $10 for a child. We know 25 people from the school went and they paid a total of $260 for the tickets. How many were adults and how many were children? Okay, when you do a word problem, you must define your variables for me. I want to know what your X stands for, what your Y stands for. If you use A for adult, Y for youth, or whatever, C for children, that's fine. You need to define your variables. So I'm going to let X equal the number, and I will put that on, so follow directions. On quizzes or tests, I will tell you, define your variables. And the other thing is I need you to use algebra to do this. I totally get that you can mess around with numbers and figure out how many adults and how many children. I get that you can do that. However, I'm not teaching, math mess around with numbers class. I'm not teaching college mess around with numbers class. I'm teaching college algebra, so I need to see you use algebra. All right, so we have some information here. We know that there are 25 people that attended the concert, right? So the 25 people, well, if I take the number of adults and I add the number of children, I should have 25 people. So that's going to be my first bit of information, right? So that was just kind of that first thing that I can glance. So I know tickets are this much, and I'm going to deal with that in a moment. But if I look at this sentence right here, this sentence right here really tells me kind of what I want to know, right? So I know 25 people from a school attended the concert. So there's my 25 people attended the concert. Then it says they paid a total of $260 for the tickets. So this is the number of people, right? This first equation. Now let's talk about money. How do I represent an equation with the amount of money? Well, it's going to be $12 for an adult, $12 per adult. So 12 times X is going to be how much I'm paying for the adults. Then how much am I going to pay for the children? 10 times Y, right? And what is this all going to equal? $260. I hope that makes sense. So once you solve that, we'll have our answer, but I have an equation for money. I have an equation for the number of people. What do you know, guys? I have a system of equations that I can solve, okay? So I'm going to just because we're already at like 34 minutes, I'm going to let you solve that. You can do that with elimination. I would do elimination. I would multiply the top by a -10. And then, well, if I did that really quick, if I multiplied the top by a -10, that would get rid of my y's. That would leave me with 2x. This would be a negative 250 plus 260 is 10. So that tells me that x is 10. And then if I look up here, that tells me that y is 15. Okay, and then of course you need to state your answer in a sentence. So there were, what, 5 adults and 15 children. Okay, you guys, so I know writing in a sentence, I hated doing it. I hated doing it in class, but as a teacher, sometimes I feel like you guys are good at maybe solving problems, but not really understanding what your answer means. And sometimes you don't really think about if your answer makes sense. So if I force you to write that in a sentence, sometimes that helps you kind of see what makes sense and if your answer really is valid. So I'm not asking for Shakespeare here. I just need a sentence. But I do need a capitalization, punctuation, and, you know, all that verb and noun stuff. Make sure it's a sentence. So, all right, let's do another one. That was kind of fun. I kind of want to do another one here. Let's look. I am going to steal one from your book real quick. So here's a quick example. At a certain store, a mix sells. Oh no, that's not what I want. Let me just. Sorry, you guys. I'm trying to make this not write as much, and so I'm just going to give up on that and just tell you. I'm going to just do what your book says. So this is also kind of silly. At Max's Munchies, which apparently, I don't know, is a store for the munchies. Caramel corn. I'm not going to say anything else about that. Caramel corn, worth. This is a good one to do because this one is always one that everyone messes up. $2.50 per pound is mixed with honey roasted mixed nuts. This is making me hungry. I don't want to write. Well, that's all right. We'll do that. Mixed nuts worth $7.50 a pound. Okay. Okay, in order to get, and this is all in order to get, 20 pounds of a mixture worth $4.50 a pound. All right, so let's finish writing this and then we'll talk about what actually is going on. How much of each snack is used? Whoops. Sorry about that. All right, sorry, that probably was a little bit weird. I messed up my screen capture here, so that probably broke it up a little bit. But how much, of each snack is used? All right, so here's what we have going on here. Okay, let's try and figure out what we have going on. So at Max Munchies, we have caramel corn, and that caramel corn by itself sells for $2.50 a pound. And then I have a honey roasted mixed nuts, which is worth $7.50 a pound. What we're gonna do is we're gonna put them together in order to get a 20-pound mixture where it sells for $4.50 per pound. So how much of each snack is used? This is like, I don't know, what are we doing, right? Let's just break it down and see what we have. So I am going to let C equal the pounds of caramel corn, okay? And then, I don't know, we have honey roasted nuts, so let's use N for the nuts maybe. This is the pounds of nuts that I'm gonna have. Okay, and now I'm just going to figure out, I have defined my variables. You must define your variables. Now I'm just going to figure out how I can relate these together. So let's first look at how much we have, right? So I want a 20-pound mixture. So I know that C plus N must equal 20, okay? So this is the amount. This is the pounds of each mixture. Now I want an equation that talks about the money. So we have to be careful with this one a little bit. Again, I want to talk about the money. Show me the money here. I want to talk about the money. So how much, right, is the caramel corn? The caramel corn is $2.50, so I'll just do 2.5 right? And how much is the nuts? $7.50. So look at what I have here. I need you to think about units a little bit. I have money times pounds. This is money per pound, and this is pound. This is money per pound, and this is pound. So if I just put here $4.50, this isn't going to make sense because my units aren't going to match up. Again, I have money per pound times pounds. Here I have money per pound times pounds. Here I just have money per pound, and I don't have it times pounds. So it's $4.50 for how much? 20 pounds. So you have to remember to get that pound right there. Look at how my units must meet up. Okay, I hope that makes sense. You have to multiply by that 20. This is going to be $4.50 times the 20 pounds that I actually have. So you see we have our equation here. Let me get rid of some of this stuff right here because that's a little bit confusing. We have our, did I say mixture? I have my system of equations, and now I'm ready to go. So I'm already at 40 minutes, so I'm not going to solve that for you. But if you solve this out, I think I'll have you do that one. I think what you end up getting is you get 12 pounds of caramel corn and 8 pounds of roasted nuts. So again, this guy, again, I really like elimination, but this guy could be, you could do substitution pretty easily here. Maybe solve for C or solve for N. All right, you guys, that was a long lecture. If you're still hanging in there with me after 41 minutes, I'm proud of you. If you have any questions, let me know, and I hope that helped.